Okay, guys, just to follow up on that, I hope you watched the demonstration. I actually worked hard on that. One thing about this pandemic is it's forcing me to think of my lessons in a very different way. And I know a lot of times I'm just writing notes down it's kind of boring, but doing that demonstration online, I actually appreciated that, like figuring that out. I was like, wow, I can show them how Thomas Young worked out his experiment with this virtual ripple tank. I didn't even know that was possible. So anyway. Yeah, I'm going to use that one in the future for sure. So, all right, Thomas Young's experiment. So remember, I just want to point out a couple things. This took place in the mid 1800s. Maybe I shouldn't write in red, eh? Okay, write in black. The mid 1800s, and then he was trying to show that light will produce double slit interference like how water would do it in a ripple tank. Okay, at the time. Light was still considered a particle thanks to Newton's theory. You know, when in doubt, you go with the more famous guy, right? That's how science works. So anyway, this was a situation at the time. The early experiments failed. Okay. And it seemed like light was a particle and not a wave at all. Okay, now I already explained what happened there. So let's just take a look. At first I'll draw a picture, okay, of how it works here, and then I'll show you how he fixed it, okay? And I already mentioned this in the other video, but like let's say you have your light source here. I'll color it yellow. Here's your little light source, and then we've got our light rays that are shooting out of it. Actually, you know what? I'll make it red. Let's make it red. So here's my light source. It's colored in. Alright, there's my little red light. I know how much you guys like watching me color. It's shooting out light here in all directions like that. Okay, and I'm going to put our double slit apparatus right here. So here is a screen with, like, you know, a screen is a piece of paper. A solid piece of paper is totally opaque, okay? With two slits cut out of it right there, okay? So what happens when the light, okay, and I'll show you a beam of light sort of heading towards here. We can't see the light in transit, okay, so here you will have your wall, you know, it's usually white, okay, so you can see all the light that's hitting it. So here's your wall back here. Anyway, what's happening is, as the light hit the wall, you would sort of see two fuzzy dots. You would see a fuzzy dot here and a fuzzy dot there, and that's all you would see. But the point is, no interference. So it's just like light passed through those two holes and it made two fuzzy dots on the other side. So it diffracted, but no interference was observed. Okay, remember, when you see interference, you see many bands of bright and dark, not just two because there are two holes. You'll see, like, you know, you could see 50 bright and dark spots if the interference was working the way it's supposed to work. Okay, like we saw examples where you get 7 nodes, okay, or 7 antinodes and 8 nodes or whatever, okay, and those things that's happening through just 2 slits, okay. So anyway, no interference was seen. But here's the thing. Light from available sources at the time was incoherent. With atoms emitting waves at a random phase. Therefore, there's no visible pattern, okay, of interference. All right, so that was significant. Now the solution here, oh gosh, is to place a single slit in front of the double slit. Okay, and that's what you see in this diagram. Okay, a single slit is placed in front of the double slit, and lo and behold, when you do that, okay, here, the light, I'll write it in red, the light waves arrive in phase, okay, at those two slits. And the two slits, there's one there and there's one there, okay? And here we have the single slit right there. So that's the trick, that's the key, okay? So here is your incoherent, coherent, okay, light, okay, that light bulb. So those waves are still incoherent, but the point is when they pass through the single slit acts like a point source. And so those waves will hit the double slit at the same time. That's the secret to getting the interference to work with these sort of crappy light sources that they have. But I mean, any light source, I mean, whether you could use sunlight, it wouldn't matter. It's the same. All light sources that either natural or artificial, except a laser. That's a key difference. But they didn't have lasers back then. So this is the solution. And this was Thomas Young's answer. And then this pattern you see here is interference. You don't just get two bands, but many. Okay, so here's your interference pattern. These are nodes. Oops. Okay, these dark ones. And here are the antinodes, right? Yeah, I feel like I can't write anymore. All right, so anyway, antinodes like that. So you get bright and dark spots, not just two, many. Okay, there are two slits. So your logic might say, okay, we'll get two bright spots, one behind each slit. That's if it was a particle, that'd be true. But with waves, you get many bands. Okay, so you get these alternating bars of bright and dark light. In fact, I've got a picture here for you. This is what that pattern actually looks like. It's an actual photograph. When you take white light and you do double slit interference, the pattern looks like this. Now, white light is made up of many colors, as you know from looking at rainbows. Okay, so here what's happening is the band in the center looks totally white. Okay, but then as you migrate out to the margins, we see the separation of these colors. Kind of like Roy G. Biv, I guess. Okay, with the blue being on the interior and the red band being on the exterior of the fringes. So we call these color fringes. Okay, what it proves is because the blue ones are closest to the center like this. Okay, it proves, this shows that blue has the shortest wavelength okay, since we measure the distances between, like let's say the center and the first fringe as to be our first sort of delta x value, or x1 if you like. So like let's say we go from here to the first blue line. I'll use the color blue. So you go from here to the first blue line like that. Okay, and this is the center of your pattern. Well, that's x1 for blue. But x1 for red is way over there. So this would be x1 for red light. Okay, and if you look at the equation that you would use to find x, you would say x1 would equal n minus 1/2 times lambda. Okay, let me get this right. Xn over L, xn minus. Okay. Lambda over d, so times L. Okay, L is the distance to the screen. Okay. And that means, let me say not to the screen, that's confusing, to the wall. Okay. Okay, from the slits. That's what L is. Okay. D is the separation of the slits. These are all constants. Okay. N is the node number. Again, a constant. And so lambda, of course, is wavelength, right? So if you look at that formula, why is x1 for red bigger than x1 for blue? Well, all of these numbers are the same, L, D, and N, for both the red and the blue light. The only one that's different is the wavelength. And so what it shows is that the red one, since x1 is bigger, it has to be a longer wavelength, okay? Because all the other variables would be the same in the experiment: the distance to the screen, the separation of the slits, and the node number. They're all the same. The only difference is there's different wavelengths for blue and different wavelengths for red, okay? And so we can see here that the blue or the violet has the shortest wavelength, and then these bands of color are organized by wavelength, okay? The only difference is, like, the green one is getting obscured. Like here we have a white bar in here. That's where green should be. So green is right in the middle of the spectrum. We're not seeing it. It's getting obscured with the blue. It's combining with the blue to produce cyan. So we're just not seeing it there. We do see some other green bands further out, but green is definitely shorter in wavelength than red. All right. So anyway, so cool, right? So now we know that if we arrange the colors of the rainbow like this, here I'm just going to write red. This thing is not cooperating. Roy, G, B, like that. This is longest wavelength to shortest at violet. Okay? And so it's so cool. You do this experiment and you can see the different wavelengths. It's amazing. Now, by the way, therefore, since we see interference like this proves without a doubt that light is a wave. And Newton's theory, which was taught in schools up to this point, was totally falsified. Therefore, Newton's theory is false. Okay, case closed. So that's why this experiment was so important. Now I wanted to give you an example of a question, and then we'll end it there. Okay, so it says here, red light is shone. Like, we're going to do this experiment with the laser, but I'm not going to do it today. I'm going to do it tomorrow, because it's getting a little late today. So it says a red light is shone through a double slit apparatus and then projected on a wall 2 meters away. The spacing of the dark fringes on the wall is 2.544 millimeters. What is the wavelength of the light? This is so cool, right? Like, we can actually make a few measurements and determine the wavelength of of a red light like this, okay? And actually that's our experiment when we do it with the laser, okay? Now, by the way, I'm not showing you the single slit here. It's there. If you have to use a single slit. If you're not going to use a single slit, okay, in front of the double slit like Thomas Young did, then you need to use a laser beam, okay? Now, fortunately for us, we do have lasers, so we don't have to bother with the single slit. So let's say this is a laser, okay? Or it's a red light and it's got a single slit in there. It doesn't really matter. We get the same pattern, okay? And I just want to point out a couple of things to you here. You get the interference, so these bands of interference. This is what it looks like on the wall. The pattern on the wall of light looks something like that, alternating bright and dark bands, okay? So I'm going to tell you how the variables work here. So let's just get a couple things straight. L is the distance from the slits to the wall, okay? So we call this distance L. Okay, so L is that distance. D is the distance between the two slits. So that distance there is D, okay, between these two things. The separation, here we've numbered our antinodes. We can number the nodes too. That's n equals 1, n equals 2, n equals 3, and n equals 4. Remember, there's no n equals 0. And then on the other side, n equals 1, n equals 2, and n equals 3. So we can number our nodes. Now, delta x would be the distance between two nodes. Okay, so or two antinodes, it really doesn't matter. So like, let me show you how you would measure delta x. I'll use my rainbow color. Okay, so if I want to measure the distance between two antinodes, or two nodes, what I would do is I would go from the edge of one antinode to the same edge on the next one. And this distance here would be, oh, that's not very clear. Let's make it blue, would be delta x. Okay? All right, so now that you've seen all this, there's a few notes there in the picture for you. Okay, now we use our data here. Let's solve the problem. Let's find the wavelength of this red light. Okay, so I'm just going to write down the given information. First, it says here, I'll zoom in on the question, light is shone through a double slit and projected onto a wall 2 meters away. So 2 meters away, that's L. Okay, the spacing of the dark fringes on the wall is 2.544 millimeters. That's delta x, that's the spacing. Okay, they're asking us for the wavelength. Okay, and that's it. They gave us two pieces of information. They're asking for the wavelength. All right, so we're going to use this formula. Delta x equals L lambda over D. Okay. Oh, shoot, I forgot to tell you what D was. No, we need to know what D is. Okay, I'm just going to say note D. The separation of the two slits has to be known. I believe it's 0.5 millimeters. I think that's right. We'll find out when we get the answer. All right, so let's do it. Now that we have all that, okay, I'm just going to put that in brackets. That had to be included in the question. It was missing for some reason. Okay, so anyway, let's solve this for wavelength. Doing a little math, d delta x over L. Okay, if I rearrange that equation. So now just plug in all the numbers. Now they do all have to be in meters, so I'm just going to say note. You must convert everything to standard units. Millimeters will not do. Okay? So, what that means is D would equal 0.5 times 10 to the negative 3 meters. Delta x will equal, what does it say? 2.544 times 10 to the negative 3 meters. L is already 2 meters. That's fine, that one. So we're good to go. Okay, let's plug all these numbers in, see what we get. So 5 exponent 3 negative times 2.544 exponent 3. Oh, sorry. 0.5 exponent 3 negative times 2.544 exponent 3 negative divided by 2 equals. I get 6.36 times 10 to the negative 7 meters. Now, I'm going to convert that into nanometers, which the textbook does very often. Okay, so this will be 636 nanometers. 1 nanometer equals 10 to the minus 9 meters. Okay, so 636 nanometers. That's red light. Amazing. Okay, so 636 nanometers is the wavelength of red light, of that red light anyway. Okay, in fact, what we would find is, I'll just say note, you could do this with any color you want, find all the wavelengths, and what you'll find is all the wavelengths you can see range from about 800 nanometers down to about 250 nanometers. Red starts out around 800 and goes to about 600 nanometers, so it's a range of wavelengths. And over here on the other end of the spectrum, you have violet, and all of the other colors are in between. So blue is around 300 nanometers. Okay, green is around 500 nanometers. Orange would be around 570 nanometers, something like that. So like you've got all the colors in the spectrum, and all these colors have corresponding wavelengths. That's so cool. And so like these are the wavelengths you can see from 800 to 250. That's all you can see, that's it. Now there's some organisms that can see a wider spectrum than we can, like certain shrimp and stuff like that. They have additional color receptors. Some insects can see ultraviolet light and so on. But really, most living things, that's basically your spectrum. Okay, so there you go, guys. Young's double slit experiment. One of the most, like I said, probably the top 5 experiments in the history of physics. It just showed, like it established the wave theory of light. And like without the wave theory of light, you wouldn't have your cell phone. Okay, like you wouldn't have your radio waves that power your cell phone, the microwave oven, and so on. And like, I mean, think of what radio waves have done for us. Wi-Fi is a radio wave, right? So like when you think about it, wireless communications of any kind, how important that is in our world. Well, when Thomas Young did this experiment in 1850, you can trace the history of all this technology that we have today that's based on wireless communication. You can trace it back to that discovery, right? Like that was the beginning of it. And then we discovered more, okay, after that. So we'll get into that later. So that's it for today, and I hope you have a good one, guys.